Hey space enthusiasts, and welcome back to the channel. Today, we're rocketing off to the king of planets, Jupiter, to unravel a mystery that has stumped scientists for decades, the incredible, mind-bending puzzle of its equatorial jet stream. Picture this. You're standing on Jupiter's equator. Well, not literally, since it doesn't have a solid surface, but let's imagine you're floating in its upper atmosphere. You'd be swept up in a colossal river of wind, a jet stream roaring along at over 300 miles per hour. That's faster than a Category 5 hurricane on Earth, and it's a permanent feature of the planet. But here's where it gets truly weird. Jupiter is a speedy rotator, completing a full spin in just under 10 hours. You'd expect its atmosphere to more or less keep pace. But the Equatorial Jet Stream doesn't just keep pace, it outruns the planet itself. It's moving faster than the deep interior of Jupiter is rotating. This phenomenon is called superrotation, and it's like a cosmic magic trick. Think about it, what force is continuously pushing these winds to go faster and faster, and how has it kept them so stable for the centuries we've been observing them? On Earth, our winds are primarily driven by solar energy. The sun heats the equator more than the poles, creating temperature differences that drive atmospheric circulation. We might assume the same for Jupiter, right? The sun's energy hits the equator, heats the gas, causing it to rise and flow towards the poles, and then the planet's rapid rotation, the Coriolis effect, whips these flows into east-west jet streams. It seems logical, but there's a massive problem with that theory. Jupiter is over 5 times farther from the sun than Earth is. It receives only about 4% of the solar energy we do. When scientists ran the numbers, they found that solar heating alone is far too weak to power the monstrous jet stream we see. It's like trying to power a freight train with a couple of AA batteries. The energy budget just doesn't add up. So, if the sun isn't the primary driver, where is all this energy coming from? This question forces us to look deeper, literally. Unlike Earth, Jupiter has a powerful internal heat source. It radiates about twice as much energy as it receives from the sun. This heat is a remnant from its formation billions of years ago, a slow, continuous cooling process. This internal furnace is like a giant engine churning away in the planet's core, and it must play a crucial role. So, the new leading theory is that the energy comes from within. The idea is that heat from the interior creates massive, churning convective currents, like water boiling in a pot, but on a planetary scale. These deep, turbulent motions could transport energy and momentum up to the cloud tops. As this gas rises and moves, the planet's rapid spin organizes the chaos into the orderly, powerful jet streams we observe. It's a beautiful idea. The planet's own internal energy is fueling its extreme weather. This brings us to the next part of the puzzle, stability. How do these winds, born from deep chaos, maintain such a stable, high-speed flow for centuries? The Great Red Spot has been swirling for at least 350 years, and the jet streams appear to be just as ancient and reliable. Recent data from NASA's Juno mission has given us our best clues yet. Juno's instruments can peer deep beneath Jupiter's colorful cloud tops, measuring its gravity field with incredible precision, and what it found is astonishing. The jet streams aren't just a thin weather layer, they are incredibly deep. The patterns we see on the surface extend downwards, perhaps as far as 2,000 miles into the planet's interior. That's hundreds of times deeper than Earth's oceans. This discovery is a game changer. It suggests the jet streams are not just surface phenomena, but are deeply rooted in the planet's structure. Imagine them as giant, spinning cylinders of gas, nested within each other and extending far down into the planet. The sheer mass and inertia of these deep structures would make them incredibly stable. They're not just being blown around on the surface. They are fundamental to how the planet itself rotates. This depth helps explain their power and longevity. The convective turmoil from deep within the planet feeds momentum into these massive cylindrical structures, and once they're spinning, their immense inertia keeps them going. It's like a colossal flywheel system. The deep roots act as an anchor, preventing the winds from easily changing speed or direction, locking them into the stable pattern we see today. But wait, there's another twist. As these jets plunge deeper, the intense pressure changes the very nature of the gas. The hydrogen that makes up most of Jupiter gets squeezed so hard it starts to behave like a liquid metal. This electrically conductive layer creates a powerful magnetic field. The thinking is that this magnetic field might act as a brake. As the jet streams try to push deeper into this metallic region, the magnetic forces could drag on them, slowing them down and ultimately stopping their descent. So, the jets might extend 2,000 miles down, right to the edge of this magnetic braking zone. It's a delicate balance between the churning energy from below pushing them and the magnetic field holding them in check. So, what have we learned? Jupiter's super-rotating jet stream is a majestic puzzle, and we're finally starting to put the pieces together. It's not powered by the distant sun, but by the planet's own primordial heat engine. The churning chaos from deep inside is organized by the planet's rapid spin into vast, deep-rooted cylinders of wind, and their incredible stability comes from this immense depth anchored in the planet's interior and possibly braked by a magnetic field. Studying Jupiter's atmosphere isn't just about understanding a distant planet. It helps us understand the fundamental physics of how atmospheres work everywhere, including here on Earth and on the exoplanets we are discovering around other stars. Jupiter is a natural laboratory for extreme weather, pushing the boundaries of what we thought was possible. The Equatorial Jet Stream is a testament to the complex and powerful forces that shape the worlds in our solar system. It reminds us that even in our own cosmic backyard, there are still profound mysteries waiting to be solved. What do you think is the most fascinating part of this Jovian puzzle? Let me know your thoughts down in the comments. Thanks so much for joining me on this journey to the heart of a gas giant. If you enjoyed this deep dive, don't forget to hit that like button, subscribe for more space science, and ring that notification bell so you never miss an update. Until next time, keep looking up.